I'll use that in just a minute.
Okay.
I'll address you this way since you know who I am, or will know who I am. I'm a physicist who's been in this business for a long time. My first experience was in believe it or not, 67. Most of you were around then, but not necessarily all of you. Anyway, where were you in 1957? Any of you remember?
Yeah.
Okay, that was an important year.
That's right, because I was born in 57.
That's what makes it important. Okay. Anyway, it was important because, okay, a bit of history. This is just to make sure that you're paying attention, first of all.
Click on that picture. If you yeah, you still can. Which one?
Bill, it's May 18th, it's a $15 registration fee.
Any more? Let's do this one. Well, yeah, yeah, that's what I'm doing. How do you click? Click on this.
Go into the Patriots track company.
Yes, they're doing it as well as they can. How do I click on this?
Use the mouse and
One more try.
It's how we do.
Uh-oh, I don't like that one.
Thanks for coming.
Okay. We're going to talk about artificial satellites, not real natural ones. But in order to get you oriented, we all know what a satellite is. It's a hunk of material floating around, in this case in space, around another hunk of material, namely the moon around the Earth. It's been there for a long time and has certain functions that we all know about. It's curious that this artificial satellite concept came from Newton, which is one of those guys who we usually choose to ignore. But he was one formulating the concept of gravity a long time ago. And he thought you could fire a cannon from a mountaintop, and if you got the right speed, it would fall to the earth at just the right rate, and it would go around the earth instead of actually hitting the earth. Not very practical, but nevertheless, the concept was put forth. Now, they didn't have the equivalent of the right cannon to shoot a projectile until there was further development on this. And Goddard at WPI built the first liquid rocket. And you'd wonder, well, why is that important? Well, as a starting point, you could now make something that would go very fast and make it very high, but his only went 40 feet or so. Others have gone further. Unfortunately, the Germans also knew about this and used it in the V-2 rocket. the fuel was alcohol and liquid oxygen, and when you mixed them together and in the right geometry, you could get thrust out of it. Now, 1957. This is more than a decade later than Goddard's experiments. I remember this because I entered college, and it was in the newspapers the year I entered college. So some of you probably remember, you may not remember this particular detail, but you remember 57.
Some of us.
Feel free to ask questions if important.
Wasn't Sputnik launched on October 4th, 1957? You got August up there.
Yeah. I told you could correct spelling errors.
Yeah, we're spelling error.
Anyway, it only had a radio beacon, and it was different than most others in the sense that some engineers at Johns Hopkins Applied Physics Lab analyzed those signals, and they were able to determine the actual orbit from the radio signals, which seems a little odd at the time because there was no such equivalent technology available. It led to the transit navigation system, which was used for submarines. Only because you had to be, submarines used to navigate using starlight, but they had to come to the surface and they'd be exposed at that time. And this was, very touchy political time. But with the transit system, they could simply get just below the surface and put an antenna up and listen to the satellites and determine where they were. So it provided a military secure option for this. In the meantime, other people were studying radiation and so forth using balloon-borne satellites, partially for meteorological purposes, and then they realized there also was radiation up in space. That was actually my first involvement with space. I worked for a group that was flying the balloons. But later on, when they got, a few years later, after the transit system was developed and presumably stopped, they came up with means of putting up rockets. And as I said before up here, we had the radio beacon from Sputnik, and in January the following year, the U.S. had launched Explorer 1. So they were already working on this, but their launches were from rockets that were intended primarily for military purposes. Anyway, the communication satellites were the most obvious application for them. And they had, for example, a large balloon that they put up, which they could reflect radar off of for test purposes. It eventually became something that would go into the GPS system, but that wouldn't be for another 30 years or so. I don't know when it went up, but it was probably 1985 or so. So between 65 and 85, there was a big change. Anyway, where are these damn things? It's hard to categorize exactly how to break this topic down because it's so complicated ultimately. There are near Earth satellites, and then there are deep space satellites.
John, what do these satellites do?
Well, I'll be getting to that in just a second. The near-Earth satellites are used primarily for communications, but they can be used also for navigation. And the GPS is a perfectly good example navigation. They are also used for commercial purposes, such as finding out what crops are like. They can look, they put cameras up there, and they can, by using the appropriate filters and whatnot, they can look at various parts of the earth and determine what the crops are and their status of them, believe it or not. They can tell you whether you should be picking your corn at this time or not, or maybe just avoiding it. But the primary thing that we see is probably the weather satellites. My interest has been primarily in solar observatories, because ultimately, they're near-Earth satellites, which are within a few hundred miles of the Earth. And then there are a lot of others that are much further out, tens of thousands of miles. And we'll get to later, some of them are much further than that. Most of you probably aren't particularly interested in the solar observatories and the fact that we don't know a whole lot about the sun and its operation, but we do need it. We also have a scientific interest in knowing where Mars is and what it's like, and the other planets, because we can see them with telescopes that many of us here probably have actually used for maybe your grandchildren at this stage, I guess. Some of the people are also interested in extrasolar things beyond Pluto or the Kuiper Belt, which is another set of satellites or set of objects out beyond Pluto. In terms of being low Earth, which is a simple way to categorize them, they're a couple hundred miles up, and there are a lot of them that are being put up there most recently because the technology has allowed them to make things that are small, and without going into the details of how they get them up there, they inject tens of these at a time for purposes of, primarily for communication. They will ultimately come down, but if you put them in the right orbit that's high enough up, the Earth's atmosphere doesn't have much of an effect on them, and they'll stay there for 20 years, 50 years, some further than that. If they're too low, the friction of the Earth's atmosphere will cause them to cause drag, and they'll come down within, in some cases, months, in some cases, a few years. There's the middle altitude, which has very little air or gas of any sort, and they'll last a long time. For example, GPS is up at 1,250 miles from the surface of the Earth, and there are a whole bunch of them there. And they were picked at that location for some very specific reasons, namely being able to get communications to them, for controlling where they are and correcting their orbits, as well as positioning them in such a way that from Earth you could determine where you were to within a foot or thereabouts by getting signals from 3 of them. That's a whole subject by itself. If you go further up in altitude, you can get to a point where they rotate at the same speed as the Earth, but they might in fact be, well, they're synchronized with the rotation of the Earth. So you can do various things with them. For example, if you go in an orbit that goes around the North Pole and the South Pole, you can view different parts of the Earth in a day and see all of them. There are geostationary, which are the ones that are, say, at the equator, but they stay there and they rotate at the same speed as the Earth, which good for weather and communications and TV and stuff like that. There are a couple of pictures that will show up in a second here, which, yeah, here's a better picture of this. It gives you somewhat of an idea that the Earth has a polar axis, it rotates, and you can put satellites any place you want. But they don't necessarily stay there if you don't put them in the right places. Okay, what do they have in common? Well, first of all, they all need some sort of, if they're intended to be active satellites, meaning they have power, you can send signals to them and get signals back, they need energy sources. Some of them are up there just as a passive reflector. For example, the first ECHO satellite was just a big balloon that you could look at and send radio signals off of. But they all have batteries, solar panels, and a few of them have nuclear power, very few. A couple of them in particular, because they're going so far from the sun that there's really there's very little energy from the sun to generate electricity to run the equipment. They all have some sort of orientation capability and driving force, if you want, to keep them that way. There's sun sensors which look at the sun and tell you which direction. It's kind of like a magnetic compass that we would use here on Earth. It's star trackers that can look in different directions but determine more accurately exactly where you're pointing. Some of them are also using the magnetic field of the Earth to determine orientation and, in fact, the shape of the Earth's magnetic field, which is not the way you would expect from a textbook picture. They also have equipment on them which allows you to change the direction and keep it pointing a certain way and all that. With the electricity, the sun solar arrays, they run communications two directions, and they have application-specific instruments, meaning cameras, radar, radiation detection equipment, whatever you want. And it would take months to describe all the instruments that they have there. But nevertheless, they have a lot of applications. Why do they do it? Well, like a lot of science, they do it because they can. Most of us have had some experience with doing something just because we thought it was fun. You might want to get something out of it, whatever. The other side of it is some of these things are very, very useful. The Earth observation tells you the shape of the Earth, for example. It's not a sphere. It's kind of pear-shaped, and it has divots in it and whatnot, and the high spots which you can detect. But the ones that we're most likely to be used or involved with are the communications for both military and commercial. That's where we get TV, we get radio from certain of the satellites. And we also have navigation in our cars for many cases. And the cameras themselves are not only visual, but for various wavelengths of light. They can look at the ultraviolet as well as the infrared. And you get different forms of information depending upon the color of light that you're looking at. They also use light and radar imaging for determining various kinds of features. For example, surface waves on the ocean can be determined using radar. And there's a whole, again, thousands of ways to look at it, but most of them don't have any direct effect on us, but nevertheless, that are up there and they can be done. There's also the group that looks at stuff from the solar system, namely solar physics, which look towards the sun, and the radiation that comes from it. And there are astronomers who tend to look the other way, namely look for planets and their characteristics and how they move, where they came from, what's going to happen to them, and so on. That's a little bit more involved and abstract. Anyway, I think am I going in the right direction on this? Just to give you some perspective, this is not a scale drawing, by the way. However, if you were to look at what Bernie has in his hand, it's a basketball. It's about 8 inches in diameter. And if that were the size of the Earth, and this were the moon, it would be down there, 20 feet away. And this happens to be an accurate replica of the moon. It shows the craters and everything. It's all done in rubber, so you can change it. But if you were to look for the sun on the same scale, it would be down at 4 West Main Street, approximately 1 astronomical unit away, which is a long ways. It's 93 million miles. Again, it's hard to describe where this is in terms of anything that you can put your hands on, except for something like this model. Now, if you were to and try to illustrate where the bulk of the satellites are, they'd be within the black line outlining the Earth. In other words, they're within a few hundred miles. And again, at this scale, in terms of the basketball that Bernie has, they would be within 1/8 of an inch of the surface of that basketball for the bulk of all of our satellites. So we occupy a very small portion of the solar system, but it's the important one as far as we're concerned. At least I think it's the most important one. I don't know if you have other opinions about it. The number of objects out there, this is a graph of number of items of various types and their altitude along with year. The upper right corner shows the total number of objects, and it shows something like 18,000 objects bigger than the size of your fist that are up there now. It seems like that's got an awful lot of space, a lot of objects, but there's a lot of space too. However, here are some better numbers. Some of them are actually tracked because they tend to run into each other, or they can run into each other. Some of them come down, and the scary part is when they tend to run into each other, they generate more small particles, just like to have an accident in the parking lot, you usually leave a few pieces of your car behind. It's not nice, but up there, these things are traveling at tens of thousands of miles an hour, and a small particle can do a lot of damage. Now, it's very difficult to analyze exactly what would happen, but there are instances where people are trying their best to remove these objects. There was a recent one where our company sent up a satellite to try to recover another satellite, their own fortunately, and it ran into it and created debris. It didn't bring it down, but it's prone to all kinds of technical difficulties, let's say. in terms of how much stuff we're putting up there, this picture doesn't show it, but you can see that it, starting about 10 years ago, we started putting up a lot of them, and this includes a lot of these microsats or CubeSats. Since you can launch many of them at one time, people have decided that that's what they will do, is they'll launch many of them. Because, and I'll show you some pictures of what they're like. This is an artist's conception of where some of the debris is. This is the bigger debris. And you can see the distinct ring out there, which is geosynchronous altitude, meaning they stay there and they rotate with the Earth. You can only put so many of them out there before they lose their special characteristic location in space, because if they get closer together, they run into each other. And they need to be something like a few miles apart so that they can safely and securely create a communications link with them without causing communication link with the next satellite in that orbit. And there are something like 2,000 satellites out there, which are used for TV primarily. There have been a number of these that are accidental. Some of them are, I assume, deliberate. But this gives you kind of a picture of things that happen out there that we don't necessarily make the news, at least not the news that most people read. And you can see that there are a number of things. Well, when it says 170 million bits of debris, these are things that are the size of a sugar cube, basically. And when you take 170 million of them, even if they're in a big space, they're relatively close to each other, and they're like, the good thing is they're largely traveling in the same direction. So it's only when they deviate from their defined exact orbit that you have to worry about that. But as of a few years ago, we had over 20,000 artificial objects there, and 2,200 operational satellites. Again, this is 6 years ago, and we've been launching a lot of them since then. This is a typical CubeSat. You're not likely to have seen this picture before, although this is what a good percentage of the small satellites are. They're small enough to fit on your kitchen table. You can see by the person's hands that they're not very big. But you can stack these together. You can put 16 of them in an 8x2 array or larger and launch them together. And the idea is that you can make one of these units with, for example, a camera, and another unit next to it with a radio receiver, and another one next to it with a small radar unit, and so on, depending upon what your interest is. And you can link them all together so that they have communications as a single unit, but you built them as a small piece. There are limits on how big you can build these, but I've seen them that are 16 units total. And they're cheap to build. We could afford, this group here could easily afford to put a few $100s in and get one. You know, if we each put in a few $100s, we get enough to build one of these satellites, if you knew how to design it, or had someone that had a design that you could just buy. Anyway, they tend to have a short life. They're put in low Earth orbit because that's cheaper to do, and because they're small, they don't have a great deal of range for them. That is, the level of sophistication of the instrumentation or the cameras is not particularly high, but they serve some purpose. There are military satellites that use systems like this. It's a little scary because they can be in civilian hands, not that necessarily the military ones. Now, back to what I originally got involved with, which were larger satellites. This is a modern configuration of a satellite. It consists of a power panel, solar array, a flat thing out to the side, which generates electricity for the rest of the satellite. And it can rotate about an axis in order to keep it facing the sun and maximize the amount of power. Because as it goes around the Earth, it doesn't necessarily the body doesn't necessarily face the correct direction. But for communication purposes, they need to be able to orient to radio antennas or look at a certain part of the Earth, even though they're traveling around the Earth. It gets to be a very tricky navigation problem issue. This might be the size, the panels there might be the size of one of these tables, just to give you the scale factor. And they're folded up along what you see as the 4 hinges there at launch, and then they're unfolded once they get up there. Sometimes they're spring-loaded, and they're more sophisticated mechanisms. I have to say this, the scary part is that some equipment that I'd worked on would have to be located right near where the hinge was, which is also where the explosive charge was unfold to allow the spring to unload. So the equipment I worked on and other people had in that same area had to be able to withstand the shock from explosives. Not huge explosives, but nevertheless, these are delicate pieces of equipment. The satellite body itself might be the size of a couple of these tables stacked up here, just to give you the scale factor. This is a different one. This has 2 antennas, the big circular devices, and they can be oriented independently, and it has 2 large solar panels, which are the rectangular arrays. This is the TDRS constellation. This satellite, in contrast to the CubeSats, would barely fit in this room. It's big, and you can imagine, since the satellites have to be launched, this was well folded up, and then the round antennas had to be collapsed in order to fit into the satellite launch facility. But nevertheless, there are 10 of these up there, and they are used for military communications primarily, and they provide secure communications because the body of the satellite has a very sophisticated electronics communications in it. This one doesn't have a satellite that goes with it, but this is an example of what a deep space probe can do. This one was a Cassini mission, and it is out at Saturn taking pictures such as this one. It takes a lot of pictures, and you see features in this that you can't see from Earth. For example, these rings are like 100,000 miles in diameter, but they're less than the height of this in thickness. So they're extremely thin. And if you look at them from the edge, you don't see any lumps. Except in maybe a few instances. I thought there's a little lip that you see under where the N in Saturn is, if you look carefully, which is an asteroid there, or a sub-satellite if you want. But the colors are representative of the kind of material that's in those rings, and most of it's ice of various sorts. Now, we're going to get to what I'm calling the Billionaires Club. A number of satellites have been built that are extremely large by comparison. Hubble is one of them. Went out there in what, 1990 by the shuttle. It is far bigger than this room. It had a problem. The mirror, as we all know, was made to the wrong shape. But fortunately, there was a young woman astronomer who could look at the images and realize that there's a correction for it. So, although they used the wrong tooling in order to measure the telescope mirror when it was on the ground, and they couldn't find an error in it because it was a wrong error, wrong shape. They took a money-saving approach and didn't use a secondary test for the mirror, which would have revealed the discrepancy. But nevertheless, they were able to determine how to correct the mirror and build a set of optics that they put in place using the shuttle. And now it works perfectly. It's absolutely amazing because of the size of the mirror is about the diameter of, actually it's about the size of the screen that you're looking at. And they have a replica of it down at the Smithsonian in Washington without the coating on it. A little side effect. I was at a conference in San Diego quite a number of years ago, having dinner, and I ended up talking with the guy at the table next to me about lobsters in Maine. Seems a little disjointed, but he happened to be the guy that designed the structure that holds the whole telescope together. And this is after the fact. So I've run into a few people that had significant impact there. Oh, by the way, the flap up at the top was to protect the mirror and the innards of the telescope from dirt while it was being handled while it was on the shuttle. And that flap opened up after it got up there. They have since updated the arrays, and they're very large now. Anyway, it's been a spectacular success. I'm sure you've all seen images from it. And now we go to another one which is more current. I'm sure is there anyone that hasn't seen these pictures? This particular picture of this particular one. No. It is a large telescope. In fact, it's so large they had to make it in pieces and put it together. Each of those, and it had to be folded up so that they could launch it. This one would not fit in this room because if you look carefully, I don't see any people in this particular picture, but here you can see the relative size of the people versus the individual mirrors. And they had to fold it this way in order to get it into the launch vehicle. And then once it got up there, they had to unfold it. here's a better picture giving you the scale of it. Each of these is a hunk of beryllium, a beryllium alloy, because it has certain characteristics that make it desirable. It's lightweight, stiff, you can form it, create a great surface on it, and they can put a gold coating on it. And the gold coating is primarily because it's intended to look at the infrared, or the red portion of the spectrum, which gold reflects very, very well. But it doesn't look all that reflective to our eye, because we see the visible part of the spectrum. It's amazing also because once they put it up in orbit, they then have to adjust each of the mirrors individually to focus at exactly the same point, which means at some spectacular resolution, they move these in the same spot. And they did this for all of the mirrors there, and then it has to stay there as well. Because if they move, then you lose the focusing properties. But it's been spectacularly successful in doing this. They had to build special rooms in order to do the metrology for each of the individual mirrors. And I don't know, it's hard to believe, even at the level that I've been involved with these things, that they could do it. Again, I was at the same conference of specialists when they were talking about building this maybe 25 years ago. And the biggest issue seemed to be, how do you make hinges that are that good? Because if you have to fold this thing up, that's one thing, but then have to unfold it and get it to the same position, it's an entirely different problem.
John, there was a website you could watch them actually.
Pardon?
There was a website that I watched, I forget how many weeks or a month or so, and they unfolded it and were doing each, you could see the progress. There was a chart and you could actually see that that's about 3 stories high and about as big as a basketball court.
Yeah.
Yeah. It was fantastic watching it.
There's another feature here which doesn't show up here. Yeah, it barely shows up here, but at the bottom, there's a large reflector. It looks like a big sheet, but that's intended to prevent any energy from getting to these reflective surfaces, which would be thermal input and cause distortions. That is the size of the tennis court that you're talking about, but they're comparable. And how do you unfold it? Because it's not just a single sheet. It's something like 20 layers of material which are unfolded separately, and they had to do this testing in a clean room. And then they had to fold it up again to be able to get it
They're
into
gonna unfold that out in space, right? Well, the thing
Pardon?
is, they're gonna unfold it out in space
Yeah,
while the thing is moving at how many thousand miles?
doesn't matter, there's no air out there. You don't have to worry about it flopping in the breeze. But it's out in space,
Well, there's very little air. It's,
there's no air.
Space is about the side of the moon.
This is,
But in
Uh,
regards,
I don't remember where this is right now, I think it's at L1.
L2, I thought.
Yeah, this one is something like 1 million miles from the Earth. So it doesn't, it's
It's in the
well away
L2
from the
orbit.
Earth's atmosphere.
It's in the L2 orbit, it says.
Is it L2?
Yeah.
Yeah, okay. We refer to these things nicely as L1 and L2, but there are 3 and 4 as well. Question?
Yeah. I guess that this satellite is also extraordinary different as any other satellite, because the other satellites what you mentioned are turning with the Earth, basically.
Yes.
While this one is still standing
Yeah.
in the, so that is very dangerous if everybody
Yeah.
turns in one direction.
I'll go back and
this
I'll
still stands there.
elaborate, that's a good point.
Yeah,
If you were in this picture, this is a static picture, and these satellites are all moving around the Earth. Except for those that are up in this dark ring, which are moving with the Earth. The Earth is, this whole set of materials is now rotating around the sun. But somewhere out on this drawing, I guess it would be over out here in the field, there's a point towards the sun which moves with the Earth around the sun. And it stays there. And there's a particular configuration of Earth gravity's field and the sun's gravity field that match. And when they match, you can sit there and you don't have to do anything. Actually, you do a little bit. But there's also a couple of other spots around the satellite, around the Earth's orbit, where you can park a satellite. There's one which I haven't gotten to yet, which is between the Earth and the sun by 1,000,000 miles. And there's the one that we were just discussing is about 1,000,000 miles away from the Earth, away from the sun. And the intent there is because it's looking away from the sun and it's actually in the shade of the Earth, so that it gets minimal energy from the Earth, and therefore it can stay cool and work better. There's another one which is a little different, which we'll get to in a minute. Yeah, this one is facing away from the sun. And the idea is that and you don't see it in this picture. No, you don't. See where the crane is? About where this crane is a point where this set of arms fold out. And the telescope, the reflector is here, but the instrumentation ends up over here. And this folds out after it's in orbit. The energy from the sun, from deep space, is reflected off of here. It goes through some other optics and it gets to the instrumentation that detects it, creates the images. So there is a movie you can find that shows it actually happening. But this reflector here is to prevent any energy from getting to the cameras and instrumentation that's up here. I didn't bring movies. Anyway, it is.
Well, there's no atmosphere.
Pardon?
Well, there's no atmosphere, so you wouldn't you have some photons and things that at the size that this thing is that would impact and cause like a wind of some kind?
Well, I can't say you don't have anything, but there's the solar wind if you want. It's everywhere.
Yeah, so that's what I'm thinking, and folding out this thing, don't they have to compensate that? And they're moving it, what, 10, 20, 30,000 miles an hour?
I don't have that number offhand.
24,000, I think it's 24,000.
But it's still in vacuum. You don't care.
Okay. So
You haven't been playing in a vacuum very much lately. Not a physical.
Let's take a quote on that.
I'm just thinking, you know, there are little specks of things that are out there
Yes.
that might be moving at a different speed than that this is moving at.
Yeah.
And, you know, if it's just atomic particles, whether they just be hydrogen protons or something, or photons or something, this thing's moving at 20,000 miles an hour, 24,000 miles an hour.
Be careful. Photons always move at 100 86,000 miles per second. No, that's not right.
Speed of light.
Speed of light.
186,000 miles a second.
Yeah, so if this is going against it, I mean.
No, not enough to cause any damage.
Not enough to cause any,
Yeah.
okay.
But,
You can sleep tonight.
there are instances, and I can, I'll get to one a little bit later. Yeah, in space, you do have, when you're near Earth orbit, or reasonably close, you can actually get particles striking these sensors or satellites. In general, they don't do much. I have two stories I can tell, but that'll come up a little bit later. But yeah, there's very little out there, I don't know, 100,000 protons per cubic meter or whatever it is. It's not much. So they really don't worry about it. But this is the largest satellite that we've ever put out there. It also carried a substantial price tag of $8 billion. But it's doing things that you could not do in any other way. In space, the dust out there will scatter the light a little bit, and it scatters the infrared light that this looks at less, so you can see further in a dusty environment. Okay, that's all I can say. Again, it's intended to work for quite a while. It seems like it will work for quite a while, but it's only been up there for a couple of years, so we barely touched the surface of what we might find. We're not expecting to find aliens. At least I'm not. I think by the time they found them, they won't matter. Now, this is when it was folded up, and these are, in fact, they're putting one of them in place, it appears. That's on the crane. This is all done in super clean rooms that are a little bit bigger than this room, maybe twice the size of this room, and 4 times as high. And that's why the people are wearing the bunny suits for minimizing the dust and debris and spittle and whatever else that might be out there.
Is this
Now-
NASA that did all this?
Pardon?
Is this NASA that did all this?
This one is NASA, yes. NASA also works in collaboration with European Space Agency. Now, here's another one, which is in this $1 billion class, which is an X-ray telescope. It is so big that you can barely fit it into the shuttle. But it is that way because at the front end of this, there are a series of special optics, which are reflecting optics in the shape of basically cylinders, because X-rays don't want to go through anything, but they will reflect off of it. And due to this unique design in the mirrors, they can actually do imaging of X-rays. And they, again, it's the best thing out there. It gives you complementary information to any of the other telescopes. Now, we have my special. Well, this is one of them that I worked on. First of all, it is called New Horizons. It used to be something else, and they changed their name. It is powered by a thermonuclear, not a thermonuclear, a radioactive source that generates heat. And that heat is then converted to electricity. And the reason for that is that this is so far away from right now, it's so far away from the sun that they wouldn't get enough energy to run the radio communications with it. It is now the, I'll go back again to our analogy. There's a basketball back there that's the size of the Earth. This across the room here is where the moon is. The building down at 4 Main Street is where the sun is. And this is the equivalent of being up in Maine. It's so far away. But it's taken quite a few years to get there.
How big is it?
18 years.
How big is that?
How big? The antenna, well, the antenna is 6 feet in diameter.
Wow.
So it gives you an idea that it's manageable because they had to put it on the largest rocket that they could find. Now, this was intended to go to Pluto. It took a while to get there, but it took pictures of Pluto as it went by and transmitted them back to Earth. And we learned a lot along the way. I'm sure if you look, you can find images of a satellite of Pluto, which it took. This is also one of the billion-dollar projects that was undertaken. There's a little, again, the pointer isn't working here, at least for me. But I have to point it out. This is the heat source and your electricity source. This is the sensor I designed. And since it spins about the axis, it's a very unusual configuration for the sensor as such, but it works very nicely. This will tell you where the sun is, but it doesn't tell you the orientation this way, so they put star trackers here. This is what took the pictures of the planet Pluto and a few other places along the way. This one was tricky to calibrate because normally when we calibrate these sensors, or the sun sensors, we want to have them work at about the intensity that we see outside on a brilliant sunny day. This was way, way down in intensity. You could, believe it or not, when that was there in our test facility, you could actually still read, which says that even if you're out of Pluto, you can read the newspaper, basically. But that's because your eye has a very large dynamic range. It was a bit of a trick to test.
John, you're a sensor that's out in the Kuiper Belt now? What was that for? What did that actually look for?
Oh, it's only telling you where the sun is.
Oh.
Yeah, it's, we don't have a sensor that's doing anything else. There's a, believe it or not, a student dust counter that's out there. I don't know exactly how it works, but apparently they're picking up dust even out there. So maybe your concern about particles in the antennas and so forth is real, but they haven't noticed it yet.
But did they decide is Pluto a planet yet?
Pardon?
Did they decide that Pluto's a planet again?
No. My international consensus, which I happen to disagree with, but that doesn't matter.
But that, you mentioned it has a satellite itself.
Yeah, but the criteria, a few years ago, people started assessing whether it was a planet or not. Don't ask me why they started. But ultimately, they decided a planet was something that had enough mass that it would attract all the dirt around it. It would clear the space there, except for perhaps a moon or two. And Pluto isn't strong enough, it's got dirt around it, it hasn't attracted all the dirt, so it's not a moon. But it has its own moons. It's kind of a phony argument in my opinion, but
So did the
I'm not a
scientists,
member of the Astronomical Society, so
did the
that's.
scientists and engineers who came up with that idea, did the scientists and engineers who came up with the idea and decided it wasn't a planet, did they all sleep better that night? Did it make that big of a
I'm not
difference?
privy to that information.
It caused a lot of debate.
But this is one they're still hearing from, but it's far enough away that it takes light about 8 hours to get there and back. So you don't send it a message and expect a response right away. Now, this is one that is also exceptional, and it's a $1 billion project. But it's gonna get very, very close to the sun. I see I covered something up there which I should not have. But, it has a number of features on it which are also quite unusual. Because it's getting very, very close to the sun, it has this shield in front of it. And the shield is sort of this big. And the intent of that shield is to prevent it from basically vaporizing or overheating. The sun is reflected from it, and therefore it does not hit the rest of the spacecraft, which is cool. Because if it got hot, obviously you can't make your equipment operate at 2,000 degrees centigrade or whatever it would be at. It actually has radiators attached to the, a heat collector on the back side of this that gets pumped actively to radiators, which are these things. And therefore they radiate out into space because they're in the shade. Similar to what you would do with an umbrella. The coating on here is very, very tough. You don't see them here, but there are a series of these little gadgets which I designed, which are intended to, say, if the satellite tilts, it's actively controlled as it's going around the sun. So it's got to keep changing direction. And if that active control doesn't work quite right, then you get light going past this edge, striking a detector like this in the back, and that says you're going too far, go back. And so we have a protective device on there in a number of locations. It's a small thing, but nevertheless, it's a backup thing. It's the suspenders from a shirt or belt suspenders approach to things. The other thing that's very unusual about this is these solar arrays fold back, because if they're fully, when they're out here near the Earth or Venus, they need energy. So they have the solar arrays sticking out like so. When they're getting close to the sun, they fold them back. I don't go that far. But only these edges are illuminated, so they reduce the amount of energy going into it, and they can still satisfy their requirements for electrical power. That was particularly tough testing because we had to simulate about 20 times the intensity of the sun during our test. And there are only 2 facilities in the world that can do that.
How much current does it take? How much current does it take to do that?
Pardon?
How much current does it take to run that?
Oh, the total power is on the order of 500 watts. Yeah, it's
To what?
you can get a lot of energy out of these devices. I had to actually test some of our sensors to make sure that they would work at the intensity they needed to under the worst conditions. And I think my testing went up to like 60 times the intensity of the sun on a bright sunny day. And it worked, but I didn't leave them there very long. Because at those intensities, unless you do things right, you can actually melt the solder on the, holding it together, and the solder connections go. You don't want that to happen. But anyway, this one is, going to get to be 4 million miles from the sun, whereas we're normally 90 million miles from the sun.
Do you know,
It's not all the way there yet.
do you know about the repulsion system?
Pardon?
Do you know about the repulsion system? I'm always interested, fabulous, about the repulsion system, how these satellites orientate themselves, because that's essential. And to my physics goes so far that it's very difficult to orientate yourself in the space, in a gravity-less environment.
There are thrusters on the satellite itself.
And thrusters works how?
They can turn them on by exposing the hydrazine. They're hydrazine thrusters, I believe.
Hydrogen.
Yeah. So they act like a small rocket, but you can turn it on and off.
But at one point then they release an hydrogen, so they can only repulse as much as material is there, no?
Yeah, I mean, they're limited in terms of the amount that they have.
That's right.
In fact, there was a piece that several of us that we were involved with relating to how you use these, because it's a very tricky situation. In one case, you go past Venus, it'll be like 80% light that goes past Venus. But when you get close to the sun, you're changing the orientation.
Yeah.
So Bernie,
Yes.
could you give me a ride home?
Sure.
Okay. Yeah, I'm guilty.
All right, I owe you, Bernie. Okay. I actually, no, I don't.
Anyway, this is one of several projects intended to give close-up information to find out why the sun is as hot as it is. They don't know. They have got a lot of information about it, but they're coming to some conclusions based on localized magnetic fields in the sun that do something. But they make the outer surface, the outer part of the sun, 1,000,000 degrees, and the surface of the sun is only 8,000 or 6,000 degrees. They don't know why. This is the same satellite, and if you look at down here, what would be the waist of this, there are a couple of appendages that stick out. Those are the sun limb sensors, as they call it. Well, if the sun's limb sticks out there, you're protected. And the arrays are folded back for launch. Now, this is the one that I'm most proud of, in the sense that it was only supposed to last 2 years. It's been up there, and almost all of the other guidance equipment has failed, just because of the age, lubrication, run issues on motors, and this is where you can see the angular resolution is 2/100,000ths of a degree. So they want to keep this satellite pointing directly at the sun all the time. And it is the basis for a whole series of satellites that are also studying the sun as such. You can see a sort of a shiny rectangle near the top there, and in the lower left corner there's a cutout, and that's our sensor there. This satellite had all sorts of other failure mechanisms, if you want, but they were all recoverable, fortunately. And it's limited operations and the funding. How much longer can you spend $6 million a year or whatever, you know, to keep it operational? Yeah, it's going to be at the engineering lobby at the Smithsonian This is the, when you have solar flares, comes at a much slower rate. These solar flares are large gobs of plasma or electrical charged particles, and they take several hours to get here. But if you know they're coming, you can do something about it. This wasn't always the case. There was a massive explosion on the sun a long time ago, but it caused a lot of damage. They had electrical power lines taken down. This was at the beginning of when you had telegraph lines. They started fires. Okay, that was 100 years ago. You might say forget about it. But what happened in 1989? They had a large flare, and it caused a power system disruption. Not complete failure, but it caused disruption in the power system, even here, even though the effect was up in Quebec, and it trickled down through our electrical system. We don't know what happened, if that happened now. But you'd like to know that you had 8 hours notice. Before you get your ass goodbye. We all know that expression. Anyway,
Is it 8 hours?
that's the
That's
sum
not it.
total of what I can ramble through. I hope you enjoyed it.
I thought the
atmosphere actually,
sun is,
Pardon?
how far out does the Earth's atmosphere actually go?
Oh, depends on what you consider atmosphere. The breathable atmosphere,
Not breathing.
a few miles.
I mean, step over catch a satellite.
From a satellite standpoint, you probably be, if you're within 20 miles or something, you can still detect the atmosphere. But you probably have to go out, you wouldn't want a satellite to stay at that altitude because it would take too much energy to keep pushing it to counteract the atmospheric drag. That's why even these small satellites are.
John, do you miss going to work every day?
Pardon?
Do you miss going to work every day?
Yes.
That's good.
I think they miss me too, but they won't admit it.
John, on the Starlink, they've launched 6,000 Starlinks so far. By the end of the year, they hope to have 12,000. And by the end of next year, they hope to have 34,000 Starlinks.
How many pieces are they gonna have?
Well, just those little modules.
Yeah, I know. And when they start colliding, what are they gonna do for pieces?
They'll
They've
run
got,
out.
in the longer run, they've gotta start taking them down or design. They're trying to have them designed with features that will allow them to come down after a defined period of time. In other words, define your lifetime as 8 years, for example. And do whatever they need to make sure they don't stay up more than 8 years. Because at the rate they're going, we're not gonna have any sunlight left. That's why we put some satellites up higher.
You'll actually see a line going across.
Well, that's how.
Yeah.
you mentioned,
Yeah.
you mentioned the sun flare.
Yeah, but only in one area.
You mentioned the sun flares and you mentioned 8 hours. I thought the sun is 8 minutes away. And the sun
Yeah,
flips
but the
off.
plasma takes a lot longer to
Oh,
get
I
to
see,
it.
8 hours, okay.
The sun, yeah, we'll have 8 minutes, from when it happens, we'll know it in 8 minutes. But it'll take a number of hours for the effect to show up.
Oh, okay, okay. Oh,
It's like when you see lightning, and then you have to wait for the thunder.
thunder, yes, okay.
Same phenomena.
Oh,
So
okay, thank
the
you.
light is the photons being released by the sun, right? The light is the photon,
Yeah, from the
and this
sun.
plasma is actually
Solid
gas,
particle.
but solid
Yeah,
material.
it's a gas in effect, but it's all charged particles.
So that's not moving at the speed of light, that's moving at some other speed based on its, whatever the cause of it. Just like we said, rockets off, it's got a speed that gets past the sun's gravity.
Yeah. I also have to mention that the Parker Solar Probe that I skipped over is intended to look at, was originally intended to look at plasma from the sun. And by coincidence, Gene Parker was a friend of mine at the time. I've had a few associations with people here, but none of them are intact. Lunch?
Yeah.
They're interesting to talk about.
That Parker Solar Probe has that big shield that's got it.
Yes.
So now I'm wondering, how do any of the sensors behind the shield get their illumination? It's stuck out and the light hits them, the solid's gonna melt and ruin the...
But there's one of them that actually is on the edge of the probe.
Hey, Bob.
Or the edge of the shield.
Think quick.
And it's designed to be robust. It's got niobium antennas, or whatever they say, so they can withstand it. But most of the material that they're looking at is also diffused. It doesn't come just like light and straight from the sun. It's diffused around.
John, what kind of solder did they use? Silver solder? It wasn't tin lead solder.
Yeah, you're right.
Oh,
Was it silver solder?
in some cases, yes.
They're right.
Depends on, if we're talking about the solar arrays, that's just a conventional solder.
Really, tin
Yeah.
lead?
Because the solar arrays
correct.
don't get that hot.
Yeah, that's true.
So, if it can exist in that universe, can it exist as well?
Yeah, solder is an issue in a lot of ways. Some of it can be very low melting point, and they're easy to put on and whatnot, but, you know, there's, as a matter of fact, the very first project I ever had when I worked at Lockheed was, again, this is a long time ago. Is there any threat from lasers causing damage to solar arrays? And the simple fact is, the silicon cells that they use will take a lot of energy, and they don't do anything. But the question is, will the solder on them take it? And at the time, the most powerful lasers were 20 milliwatts. So what I looked at was, could you focus that at the distance of a satellite to a point where it would remelt the solder and release the leads? And the answer was, no, you can't. There's not enough energy there.
I just wonder, I know in computers nowadays, the chip that has hundreds of pins
Yeah.
is not soldered in, it's held in by mechanical force. And I'm wondering
Thank you, sir.
whether mechanical force is used in any of the connections.
I'm thinking the chips you're using
The
today
reality
are
is,
soldered.
heat sinking the main processor is a serious issue that they deal with. And there are special adhesives that they use. Some of them are soldered down, I believe.
Yeah, they're surface mount. John, they're surface mount components. They're actually surface mount
Yeah,
components. But you usually, something like that, you might strap it also. You might put a mechanical strap. Or the heat sink itself would hold it down too. But you do put like a conductive silver paste
yeah,
that will conduct the heat.
yeah. It's been done.
Yeah, yeah.
I've used that.
Yeah.
But still, it's a mechanical connection, based on a
Thermal
spring
resistance is gotta be
pressure.
low. The way you keep it low is keeping the area large, and the material's very thermal.
Yeah.
And then get the heat out the back.
Yeah.
So often, in fact, if you look at the insides of your computer, you'll and locate the processor, on the back side it is probably a heat sink.
Yeah.
Yeah,
Sometimes it's made that way.
and often there'll be some sort of fan or device to
Yeah.
help move the air around it. But the electrical connections are just mechanically pressed, they're not individually
Yeah,
soldered.
they're thermal compression bonded.
Well, you can leave that there.
They take,
Okay.
They're gonna do things.
they take the wire,
Oh, you leave it
this is
there,
the
okay.
pad, they take the wire and they
Save it.
put it
We're
in the
already
holder
here.
and they push it in.
It's gonna half an hour long.
I don't know if they've
Gonna go a half hour
applied any
longer.
heat at the time.
Is that?
Yeah,
I know, I mean, when I built these and I put these chips in, you
I'm
drop
just
it in and you move the spring and it holds it down
Yeah.
in the pad.
That, you need to have that thermal conduction there.
See, what has to happen, the actual materials have to kind of rub each other. Okay, they can't just be touching, they've got to kind of dig in.
I know on the phones, they,
I'm done.
take them apart, they heat them up,
Okay.
all right?